Hydrological frequency analysis using nonlinear regression with adaptive resampling.
You can read it from here. I made it shorter.
Wow.
Yeah.
Thank you.
Hello everybody. I'm Mohammed Alobaidi, work in Masdar Institute. Proud to be a member of the Earth Observation and Hydroclimate Lab under the supervision of Professor Taha Warda. We are here hopefully going to present our work in regional hydrology frequency analysis using generalized ensemble techniques. So we aim to obtain improved flood quantile estimates at engaged sites through embedding ensemble techniques in regression modeling with a certain sampling procedure that we called it sampling without replacement. And then we're going to adopt and apply a generalized ensemble approach in order to further push our estimate to be better. So fortunately, Professor Warda has also talked about flood quantile, but we can say that we can define QT as a quantile of an extreme annual flood with a return period of 2 years. And we're interested in drawing relationships between site characteristics and flood quantiles, and then extending such relationship to estimate quantiles at engaged sites. As a theoretical background to the ensemble is like generally a 3-step technique in machine learning, where you have the global sampling, the global sample regarded as the population, and you have your submodels that mainly compose of mainly describe the ensemble combined into our global model. So we basically use submodels or several hypotheses and combine them to through a combination procedure to get a global model that has a very good estimation of our variables of interest. Those submodels are trained upon subsamples sampled from our global sample through a certain sampling technique. As a data pre-processing strategy, we adopted canonical correlation analysis following the work of Shu and Warda and flood frequency analysis. CCA generally identifies the projection of high correlation between two multivariate variables. Hence, it improves the regression performance, the model that you are going to use in your regression. For our work in flood frequency analysis, we're going to use the canonical, physiographical, and meteorological variables as the inputs, and the 3 hydrological quantiles as the 3 flood quantiles as our outputs. So the first step in the ensemble is to be sampling. So our proposed sampling scheme is actually a 2-stage sampling, where the first stage is sampling without replacement from the original sample, and then we come to modify each of those subsamples by sampling without replacement from the other distinct subsamples into each of those modified samples. In the first step, I sampled without replacement from the original global sample, and then I have this mixture ratio or homogeneity level between each of those samples. We come then to our regression model. We propose artificial neural networks, with a feed-forward paradigm in a multi-layer perceptron architecture. We have a 1 hidden layer, 5 hidden neurons in all our submodels. We use Levenberg-Marquardt algorithm in the training of each of those models, and then we investigated different ensemble sizes, and each of those ensembles has different levels of mixtures within their sampling scheme. Another linear tool is the robust fitting, which is very similar to multiple linear regression models, but with a unique error function that disregards high residuals. For the combination, which is the third and last strategy in the ensemble techniques, we used for the artificial neural networks the median as a combiner for the submodels, and for the robust fitting, mean and median as combiner, all as each, both as each for the combination of the submodels. So we come then to the generalized ensemble approach, where we will identify the global models, the ensembles that gave us the best performance, and combine them into a median, through median, to get a generalized model, which you can call it an ensemble of ensembles. As a model performance assessor, we use the relative mean root square error incorporated into Jack-Knight validation technique, which is useful as it somehow independent of the data sample, because it tests for each of the data points that you're using in training all of your models. Our three hydrological variables are the at-site annual flood quantiles with a return period of 10, 50, and 100 years. They come from daily flow data of 51 hydrometric stations in southern Quebec. They all have passed the historical length, the natural flow regime, the tests of homogeneity, stationarity, and independence. For the 5 physiographical meteorological variables, we used basin area, mean basin slope, and fraction of basin area covered with lakes, annual mean total precipitation, and annual mean degree days over 0 Celsius. So I have 5 physio-meteorological variables and 3 hydrological variables. We used the results came produced by the work of Shu and Warda as our benchmark, and we were hoping to produce a better performance, a model with better regression performance. So for the validation results for the artificial neural networks with a median as a combiner came to be as the following. The horizontal axis shows the degree of mixtures used for each ensemble, and the vertical axis can show the RMSE deviation, the RMSER for the relative root mean square error for each of those ensemble cases. So you can clearly notice this oscillation for each of those ensemble sizes as the degree of mixture increases. However, the margin or the relative root mean square error becomes very close. The values become very close as the degree of mixture saturates. And also here, for the robust fitting tool, you can see relatively same trend. However, they converge to more narrow relative root mean square error values. And here also for the mean combiner, robust fitting tool, but with the second combiner. Such oscillations and such trend can be regarded to at least four causes. The first one is the nature of the tool that you're using. Here you see we use a linear tool, but in the artificial neural network, which is a non-linear tool, you can see somehow some more oscillations as related to the linear tool. The randomization of the sampling scheme we use also can participate in such in this trend. The degree of mixture also, and the ensemble size are those for identified causes. We come to our generalized ensemble approach, where we start combining the best models performance with their performances regarded as the lower jackknife relative root mean square error. We found that for those data, for that jackknife validation procedure, that combining the two best models, ensemble models, gave us a lower error. Here you can see a summary of our achieved relative error, root mean square errors, and the benchmark starts at the quantile of a return period of 10 years of 37%, but here we went down 5%, which is a really good improvement. Before that, before the generalized ensemble, it was 33%. We can conclude this work by saying that sampling without replacement improved our relative root mean square error, and the median as combiner is a good choice for the models that we incorporated in the ensemble architecture, and the generalized approach has further improved our relative root mean square error. Thank you. Thank you for listening.